We are now going to calculate a measure called the correlation coefficient, and because that's rather difficult to say, this measure is affectionately known as R. You'll see this everywhere, either a lowercase r or an uppercase r. The number measures linear association. Before we get to the actual calculation, we'll just go through a few things that it does, and then we will look into the calculation and the interpretation in more detail. The goal is to measure linear association. It turns out that we are going to be measuring based on standard units, just as we discussed a little earlier, and we will get a number that is between -1 and +1. The extremes represent perfect linearity. R equals +1 means that the scatter plot is a perfect straight line sloping up. The sign is the sign of the association. And R equals -1 is a perfect straight line sloping down. R equals 0 means there is no linear association. The variables are uncorrelated. Please take a look at this word, uncorrelated, meaning R equals 0. It means that there is no linear association. There may be associations of other kinds. There may be nonlinear associations. So it is quite important to note that the word uncorrelated does not mean unrelated. It means not related linearly. We'll see examples of linear versus nonlinear association and what you can and cannot say when R is equal to 0. So we're going to construct this measure R, and for this segment I'd like you to just look at the steps of the calculation and see roughly why they will give you a number that is interesting. To show exactly why the calculation must be the way we're about to do it takes some mathematics. We're not going to do that here, but I hope to give you some sense of why the moves are good moves to make. Before we get to calculations, what I'd like to do is draw for you scatter diagrams of variables given a specified correlation. The function R scatter is one we wrote for you. The argument that it takes is a value of correlation, so it's a number between -1 and 1. And you put in a number between -1 and 1, so supposing you put in -1, then it will draw a scatter diagram that has that correlation. This better be a straight line sloping downwards, and so it is. If instead you had put in 0.6, you now have a scatter diagram that's sloping upwards that has a correlation, and the numbers have a correlation of 0.6. Observe the units in standard units throughout, because you don't actually need to know what the units are on this side. You can just look at the scatter diagram and get a sense of the degree of clustering about a straight line, and it will help to be able to compare two values of R. So if I now ask for R scatter and I pass the argument, why don't we try 0.9? Then you can see that the new scatter diagram, which has been drawn to the same scale, the same standard unit scale, so -4 to 4 on the horizontal axis and the same -4 to 4 on the vertical, this scatter diagram, R equals 0.9, is more tightly clustered about a straight line than the scatter corresponding to R equals 0.6. We say that R measures the degree to which the points are clustered about a straight line. Which straight line will be coming up in the next few lectures. It's well worth looking at R equals 0. That is one scatter diagram where you see no linear association. That's a blob. But that is not the only kind of scatter diagram where you see that kind of association. Indeed, all of these examples show you one scatter diagram that has the specified correlation. There can be many other shapes. But this blob shows no linear association, and indeed, if I look at that blob, I don't see any kind of association at all, really. As I change values of x, I don't see much change in values of y. Just not much going on there. All right. So what we're going to do now is try to calculate, given two variables, x and y, so a set of points, we're going to try and calculate r. And we'll do it in the context of an example with just a few points. So this table has 6 points in it. And I say points because each one is an xy pair. So x equals 1, y equals 2, x equals 2, y equals 3, and so on and so forth. 1, 2, 3, 4, 5, 6 points. Here's a scatter diagram of the points. And based on what you know so far, you'll agree with me that that r for this scatter diagram should be positive. There's a general positive trend, but it should not be plus 1. It looks as though somebody started out with a perfect straight line and then broke it. Looking at this, we should expect r to be positive but not 1. How are we going to go about calculating r? We are going to first convert x and y to standard units. So we apply our standard units function to the x array and as well as to the y array, and augment our table T with columns x standard units and y standard units. And now the table looks like this. This column of x's has been converted to standard units, as has this column of y's. Here is where the main move comes in. What we're going to do to calculate r is multiply the corresponding standard units. Let's just do that first, and then we will see why that is a good move to make. So we are going to augment this table by another column that contains the product of these two columns of standard units. So standard unit product is an array that is obtained by multiplying this column with this one, and then we augment T with a column called product of standard units, and that has those products in it. And now we have the product of standard units. R, the correlation, is the average of these products. R is the average of the products of standard units. I look at my table, I look at the product column, and I take the average of that. That's R. So what did we get? We got R equals about 0.61, 0.62. Does that make sense? Well, yeah, we had looked at these data and we said we would get a correlation that was positive but not 1. That's what we've got. Now, I understand that there might be burning questions as to why did we take the products. And really, for a complete justification, you'd have to do some mathematics. But there is one thing that you can see here that makes the product an interesting thing to do. Look at this xy pair. What is it about this line that tells you that both x and y were below average? That's the signs of these two standard units. X was negative in standard units, as was y. When you multiply, you get plus. Here, both values were positive in standard units. When you multiply, you also get plus. You only get minus when one of the variables is above average in standard units and the other one is below. This helps R get the right sign. If the variables are positively associated, then above average values of one tend to go with above average values of the other. Positive standard units of one tend to go with positive standard units of the other. When you multiply, you get a positive result. But also, negative standard units of one tend to go with negative standard units of the other. When one is below average, so does the other one tend to be also. So negative standard units for x and y tend to go together, and when you multiply, you also get plus. So the net result, if you have a scatter diagram that shows positive association, the net result is that R comes out plus. Whereas if the scatter diagram shows a negative association, then above average values of one go with below average values of the other. That means plus standard units for one of the variables go with minus standard units of the other in general. So when you multiply, you get negative. And then, wonderfully for us, the simplest thing done to those products, just taking the average of the products, gives you an interesting measure. As with standard deviations, we are going to want to compute correlations over and over again. Since we started out by writing our own standard units function, we can also write our own correlation function. So we'll define a function correlation that takes 3 arguments: a table, the label of the x column, and the label of the y column. It extracts the x column of the table as an array and converts that to standard units using our standard units function. Does the same thing to y. So we have 2 new arrays called x in standard units and y in standard units. The function returns the average of the products of standard units. That is what R is, the average of the products of standard units. So we'll define our function, and then we will apply it to various tables and variables. As a check, we will apply it to this table T and to the columns x and y, and we better get 0.617 whatever, otherwise we made a mistake in our function. Good. For our table T and columns x and y, we get the right answer. If we look at the SUV table and we look at the correlation between fuel economy, miles per gallon versus and price, then we get, our function tells us, we get minus 0.667 roughly. Minus. Should it be minus? Let's go back and look at the scatter diagram. This was it. You had miles per gallon and price, and the trend was downwards, so negative association, yes, makes sense, and should not be minus 1. Ends up being about minus 0.7-ish. It's actually really hard to look at a scatter diagram and say what the correlation is. It's really hard. Well, unless the correlation happens to be 1 or minus 1. It is very hard. What you can do is, if you have 2 scatter diagrams that have been drawn on the same scales, you can perhaps compare the correlations. Though even that can be tricky. But it's really hard to judge correlations by eye, because our eye is so very affected by the scales that have been chosen. So it helps to have a function that calculates the numerical value of the correlation. There are some properties of correlation that become apparent when you look at the way it's calculated. Correlation is calculated based on standard units. Therefore, it has no units. It's a pure number. If you change the units of measurement of x and y, you'll get the same standard units, so the correlation will be the same. Correlation is not affected by changing inches to centimeters or kilograms to pounds. One other aspect of correlation is worth noting. Our scatter diagram of the x and y points looked like this, and this is a scatter diagram that shows a correlation of 0.617 something. What I would love to do now is to see what happens if we switch the x and y axis. So we have x going this way and y going this way. What if we were, for some reason unknown to us, wanting to switch y and x just because we can? Should we do it? What do you think will be the correlation when you switch y and x? The same? Different? Minus? Well, the first thing we're going to do is actually compute it numerically. So we will say, okay, the table is still t, we're going to do y and x, and we get what number? Ooh, we get exactly the same number. No minus sign. Let's be really confident that we should not get a minus sign. Here is the scatter diagram of x on the horizontal axis and y on the vertical. That shows a clear positive trend. And here will be a scatter diagram of y on the horizontal axis and x on the vertical. And that also shows a positive trend and the same clustering or non-clustering. What happens when you switch x and y is you flip the scatter diagram about the x equals y line. You're flipping these points about this x equals y line, that way. And so you still have a positive correlation. And indeed, you have the same correlation because you have not changed the degree of clustering at all by that flip. And that is why when you run correlation T-YX, you get exactly the same as what you got when you did T-XY. Let's summarize what we know so far about the correlation. So we have the definition of correlation, which says take x and y both in standard units, because we can see shapes and so on without looking at the original units, without taking into account the original units. It's all based on standard units. Compute the variables in standard units, multiply, and then take the average. That's R. And what this measures is the degree of clustering around a straight line. For now, you've just seen that in some simulated scatter diagrams. As we do prediction, you will see this in more examples, and you will also be able to quantify it in some way. Measures how clustered around a straight line. Operations that leave R unchanged include changing the units of measurements of the data and switching the horizontal and vertical axes. These do not change correlation. And what this does is it allows you to talk about the correlation between height and weight in a population of people. You don't have to worry about whether height was measured in inches or in centimeters. You don't have to worry about whether you should say the correlation of height and weight or the correlation of weight and height. They're exactly the same thing. And that's a nice property, because then you can use this correlation without getting bogged down in units or exactly what choice has been made for the two axes. It's up to you.